Welcome friends again. In this week, we tried to learn about the polymer 3D printing and we explored some of the aspect of the polymer 3D printing, which is basically fused filament fabrication, also known as fused deposition modeling, also known as material extrusion process. So we have seen some of the parts of the printer. We learned about the build material, we learned about the sport material, and we have seen how the filament is extruded and the strands are formed and 3D printed parts are available on the screen. Now in this discussion we will talk about the some hardware parameters, some software parameters to run my printer more efficiently. So commercially, the nozzle dia is something which is basically managing or determining the width of the extruded filament, right? So it varies from zero point 0.2 to 1 mm. Like for example, if you want to make a thin section, simply I have to keep it to the minimum size, and if I want to make a thick section, I can use the larger, dia of the nozzle. Similarly, build plate type and temperature, they are also important. So there are different type of build plate that we use, maybe glass, maybe metal, or sometimes some high temperature withstanding polymer sheet also I am using, and its heating capability, that is really important, because normally the bed temperature I keep between 55 to 60 degrees Celsius. So almost all type of commercially available glasses and the metal plates, maybe of MS type, it solves my problem, right? Then specifically the extruder type, as you have seen, I have a arrangement in the liquefied zone, and some mechanical drives are there, and I am basically pushing the filament to pass through some nozzle. So the extruder type has been categorized as direct drive or Borden extruder, which affect the filament feeding flexibility. So what I have seen in my work, the direct drive is little more comfortable if you want to work on changing the filament again and again. But of course, in multiple heads, we need to work with the direct drive only. Then coming specifically to the material parameters, like the one of the most common thing is the filament dia, varying from 1.75 to 4, but commercially available as 1.75 and 2.85 mm. We required the consistency in dia, and if you have a better filament, we will have a precise control of my extruded part. As regard to the commercial available filament type, these may be of PLA, this may be of ABS, PETG, TPU, nylon. They have unique properties, like you are interested in biocompatible part, so the PLA based filaments are used. You are interested in high strength parts, like in case of your car bumpers or the dashboard, we are interested in ABS. You are interested in some food containers, the PETG is one of the solution. You are interested in, let us say, some shape memory type solution specifically for printing the polymer on cloth, or some you are interested in making some shoe sole, so TPU type material is really recommended. Similarly, nylon again for the strength. So depending upon my end user application, we can select that material. uh, and we can make our material in house also, by adding or reinforcing different type of organic and inorganic material, which basically enhance the desired property. Then the moisture content is really important, since they are the hygroscopic material, so it is always recommended to dry it to have any moisture related defects. Then coming to the process parameters, the most important consideration is given to the extrusion temperature. So this is the temperature at which the filament is melted, and this is of course very specific to the material and the application. Like I have already explained in my previous session, let us say I am interested in making some vertebra part. So only the peak is one of the acceptable material, that is polyether ether ketone, and the peak polymer is processed around 450, right? Whereas if I am interested in, let us say, the PLA, which is another biocompatible material, but not for this application, this temperature is varying from 150 to 200. So depending upon my application and user application and the filament I select, I use to work over the extrusion temperature. Then there is a parameter called bed temperature. This is of course important to ensure the adhesion of the first layer. So for the bed temperature, again different type of plates I am using. It may be of a glass, it may be of a metal. This is important because this first layer adhesion is something very important that reduce the warping of my functional prototype. Then layer height, of course, it depends upon the my machine itself. So what is the resolution and the build speed? Normally it varies between zero point 0.1 to zero point 0.3 mm. Then coming next to the print speed. So this is the speed at which the nozzle moves during the printing. This significantly affect the quality and the time of production. If I put it fast, print speed is high, the production time will be lowered, but sometimes the solidification rate has to be correlated. Similarly, infill percentage and pattern. So it basically determines the internal structure, density, and the geometry. If I put high infill percentage, I will be having a more solid part. So I have a option like putting it 10%, 20%, up to the 100%. In some of the commercial package, they call it as a solid structure. They call it as a dense structure. So basically, I can express in terms of the uh, percentage of infill, basically adding the density part. Then cooling fan speed, this is again critical. If you put more dense part, so it has to be high so that the heat is extracted. So it helps to solidify the filament, and this is really important when I am making some overhanging section, or some bridge sections are being prepared. Then retraction distance and speed. So I am interested in preventing the stringing. Specifically, once there is a known print type, basically I am interested to reduce the non-productive part while my manufacturing. Then flow rate or the extrusion multiplier. This adjusts the amount of the filament extruded. Travel speed, of course, the speed of the nozzle during non-print movement. So these are some of the common process parameters that we keep in mind while going for the printing over the uh, fused filament fabrication type setups. Then coming to the geometrical and design parameters. So some of the common parameters are part orientation. This is really important, like how I am making the part with respect to x, y, and z plane. So people have reported, like if I am putting the part normally at 0 degree or 180 or 90 or 45 degree, the significant change in mechanical properties, significant change in strength, significant change in surface finish is obtained, right? So basically the grain structure simply is affected by this. So I have to be very careful specifically about the part orientation, because this is basically going to determine the physical property of the functional prototype. Then coming to the sport structure, of course, the placement of the sport, which is of course the consumable, or it's a water soluble type condition I am using. But if I put it at certain places where uh, the quality of the part is not compromised in terms of once I will detach it, so there should not be any functional barrier over there, right? So density to aid any overhanging part, that is really important for these type of sports structure. I can keep it at lower value. Then the raft, skirt, or brim, this is used to improve the bed adhesion or basically the priming of the nozzle. Then, as regard to the environmental parameter, we are concerned about the ambient temperature, right? If the temperature conditions are not suitable, so there will be some warping and cracking. So stable conditions are required to reduce this type of warping and the cracking part. Then the humidity level, it should be as low as possible. So it basically this improves the overall material performance. Now coming to the software part, if you see, the software basically is responsible for slicing. So there are n number of commercial software available. Many are open source, which basically have a slicing algorithm, which is helping me to have a tool path planning. Then number of shells oblique parameters, so it determines the wall thickness and the strength. Then print time estimate, this of course influence the scheduling and the preparation. Then the calibration parameters, which involves bed leveling, extruder calibration. So these are critical for like bed leveling is critical for uniforming the first layer, so that my first layer is uniform. Then the extruder calibration, this ensure the correct feed of the filament. So these are really critical. As regard to the different type of polymers are concerned, we can use virgin as well as recycled PLA, ABS, PCL, PVDF, PETG, TPU, nylon, PP, PEEK, TP, etc. There is a long range of polymer that can be processed over here. Like I have already explained in my previous talk, between 100 to 300 degrees Celsius melting, n number of polymer range is available, right? So I have to be very sure that for what particular application I am going to use it, and accordingly I can select this, maybe virgin, maybe recycled. So recycling here helps us in attaining a SDG, sustainable development goals, that has been given by the United Nations in a big way. So in our polymer line, specifically for the polymer 3D printing, we can contribute for the primary recycling, secondary recycling, tertiary recycling, and quaternary recycling. Just for an idea over here, the primary recycling means I am using a mechanical way of recycling, and I am reusing my polymer, basically, let us say by melt extrusion, like a triple F process, and the same polymer with a different heat cycle, I am using it for making a functional part. Sometimes by giving a different heat cycle, the mechanical properties are compromised. So what I need to do is I need to put a reinforcement which basically enhance some of the properties. These reinforcement can be organic or inorganic. I can add some metal, I can add metal particles or ceramic particles. So if I do some sort of a reinforcement along with the mechanical way to improve some of the properties, then giving it some thermal cycle, so this adds to the second category, which is called the secondary recycling. Sometime even by the reinforcement and heating and melting, I am not able to get the required property. Then I use some chemical way of recycling. So some chemical process like depolymerization to break down the plastic, or into the different monomers or other valuable chemicals, so that the recovery of the raw material or the mixed contaminated plastic for high value reuse can be there. We call it as a tertiary recycling. Then there is a quaternary recycling. This is basically energy recovery, where non-recyclable plastics are again used for the energy recovery process. Right? Primary and secondary recycling are very commonly used in our country, but tertiary and quaternary are mainly at the lab scale level. Right? So then coming to the preparation of the material, like the steps, we are very sure from our the two case studies. I have to go for the moisture removal, I have to go for the mixing of reinforcement, checking it on the MFI, fabrication of the filament, inspection of the filament, and finally filament feed on a 3D printing setup. So this is the rheological study, like the setup is already clear to you. This is as per ASTM 1238D. Also the equivalent standard is ISO 1133. So I put a dead weight, normally like 2.16 kg. Then there is a piston. In this zone I put the polymer, a defined quantity in the granule form. From here, the output material is forced in the form of a, some extruded in the form of normally a wire, right? So how much gram in 10 minute, that we measure on a MFI setup. Then for making tensile coupon, the standard dimensions are available, as you can see on this screen. And on a typical UTM, I can basically measure the different parameters like stress strain. I develop a stress strain curve, then go for peak load, peak elongation, peak strength, modulus of toughness as the area under the curve. As you can see, for the different parametric combination, the people have reported using typical UTM and finding the stress strain curve. This is a standard sample, as you can see on the screen, for the flexible testing. So for that purpose, ASTM D790 code is very commonly used. So the dimension of the sample like 150 by 10, and the thickness, already these parameters are fixed. And then 3-point bending I can use for this. And then in this screen, as you can see, for the compression testing, a cylindrical sample have been prepared. Again, the dimensions are freezed by the ASTM code D695. And for the different combination of parameters, I can develop the stress strain curve. Like further in thermal analysis, as I have shown in my previous case study, this is the setup that we use in our lab. And we have a glass transition, we have peak melting, we have enthalpy change, we have the crystallinity value. All these type of informations are available. You can see a small video attached to this, which will be more clear, that how we are making this type of information from this particular setup. Then this is again really important. uh, I am going to show you this video in which I am taking the output from a scanning electron microscopy by magnifying it at 100x magnification, right? And capturing the image from the SEM, or even I can use an optical microscope, as you can see in this video. And after getting the output, I am going to see what is the percentage porosity and what is the grain size number. For percentage porosity, I am going to use the ASTM B276 code, which is basically through a image processing software. The software that I am using over here is the MEAS, that is Metallurgical Image Analysis Software. And as per this code, I am getting the porosity value of something 39%, right? So similarly, we can calculate the grain size number. This is as per ASTM E112. So as you can see how we can measure this on a SEM, and then using a ASTM B276 and ASTM E112, the porosity and grain size number is calculated. Now one thing we must understand, if I am having a grain size number higher, that means the number of grains per unit area are more. That simply means the grains are fine. So my material processing route, like in this case, which is a polymer printing, must give a condition in which the fine grains are formed. Similarly, when I am using B276 code, as you can see in this screen, this is basically using a data which is specifically developed for the cemented carbide. But I am using this code for the polymer. The idea is the play is of the the porous part, right, which I am capturing through a image analyzing software, right. Then there are many other open source software like ImageJ is available. We are also using the Guardian tool to get a 3D rendered image, to get amplitude distribution function, to get the peak count, to get the surface roughness also. So that can be added to this part for adding value to the final product. So that's all about the polymer printing process, from the different mechanical properties, rheological properties, morphological properties, and developing a functional prototype, and finally coming up with a product. I hope the information is useful. Uh, Please keep on watching our further sessions. Uh, Now I will be taking in coming sessions the development of the gel parts, that is basically bioprinting, gel printing, followed by metal printing, then development of sensors, and taking some of the case studies. Thank you very much. Keep watching.